Two blocks are connected by a string that passes over an ideal pulley, as shown in Figure 1. Block A of mass 4m can move with negligible friction along an incline that makes an angle theta with the horizontal, and block B of mass m can move vertically. The blocks are released from rest from the positions shown in Figure 1. The dots in Figure 2 represent blocks A and B as indicated, and the dashed line represents the surface of the incline. On each dot, draw and label the forces, not the components, exerted on the blocks. Each force must be represented by a distinct arrow starting on and pointing away from the appropriate dot. Okay, so let's start with block A. We know that normal force is going to be acting perpendicular to the plane and it will be going up. And we know that gravity is going to be going straight down. We'll label that mg. And we also know that there's a force of tension acting parallel to the incline and down. And then on block B, we know that there's going to be an upwards force of tension and a downwards force of gravity. Derive an expression for the magnitude of the acceleration of a block after the blocks are released. Express your answer in terms of m, theta, and physical constants as appropriate. So to approach this problem, we're first going to start by treating the blocks as one system. And the reason we're able to do this is because the tension between the blocks in the string is internal to the system, which means the tension forces cancel each other out, and when we treat the blocks as two systems, when we solve for tension and substitute in everything, the tension will cancel out to 0, and we will be given the same answer. So, we'll start with F equals ma, and we will, since we're treating it as one system, we will put the forces that are acting on each block, and remember we defined our coordinate system in the previous part, so we have 4mg sine theta plus mg equals m plus 4ma. And then we divide both sides by the mass, so we get force g sine theta plus g equals 5a, and then divide both sides by 5 to get 4g sine theta plus g divided by 5 is going to be the acceleration. Now, I showed you guys how to do it like this, but I figured it would also be helpful for you guys to kind of get an explanation with treating it as two systems. So I'm going to section it off and do it down here. So we'll start with fx equals max. Now, it doesn't matter if you say fx or f if you only have force in one direction, but if you have it in two directions, then you should definitely say it. But in this case, it's a stylistic choice. Also, I'm just going to label this just in case you guys get kind of confused. So this is two systems in one system, and this is block A that we're dealing with here. Sorry, I'm going to correct that. So fx equals max, and then we're going to substitute in the big M. So remember, you want to start with nothing substituted in. You don't want to have what they call magic variables. You kind of just want to have the base equations, because that also gives you points on the AP test. So now that we substitute it in, right, we get 4mg sine theta plus t equals 4ma. And now for block B, we also are going to do fx equals max. Before we substitute it in, sorry, that's supposed to be a lowercase f, or I mean m. And now we have mg minus t equals ma. If you guys are confused where we're getting these from, it's just from the previous part where 4mg sine theta is just the force of gravity down the plane, and the plane is frictionless, so there's no friction. And now we're just going to solve for t for both sides, so that way we can set them equal to each other. And now that we've set them equal to each other, we have 4ma minus mg sine theta equals mg minus ma. Now we're just going to shuffle things around a bit, so add ma to both sides, and add 4mg sine theta to both sides. So we'll get 5ma equals 4mg sine theta plus mg, and now we can divide both sides by the mass and by 5 to get accelerations equal to g sine theta plus g divided by 5. Sorry, I forgot a 4 there. Kind of important to remember that. But this was just a demonstration to show you how, you might want to do it one way or another, but in the end, they give you the same answer, and whichever way is most convenient to you is probably the best. On the axes in figure 3, sketch a graph of the magnitude of the net force as a function of the inclined angle theta for each of the following objects, block A and block B. Label each curve A and B as appropriate. So, to make this simpler, let's start with the equations of motion for each block. We know that F net for block A is going to be 4mg sine theta plus t. And then for block B, it will be, oh sorry, I forgot, I should probably label these so it's easier to see. So block A and block B. For block B is F net equals mg minus t. Now, what I want you guys to notice is that the most significant thing about the graph is where you start and end, and how the curve looks. So for F net equals mg sine theta plus t, you should have a somewhat sine looking curve. And so we're starting at 0 and ending at 90 degrees, right? So at 0, sine of 0 is 0, and you only have tension. And tension will be between 0 and mg, because at 0 degrees, right, the tension is just going to be caused by the weight of the block, mg, and the tension cannot exceed the weight of the block, so it has to be between 0 and mg, right? So, and because it's a sine curve between 0 and 90 degrees, sine is going to have a positive second derivative, right? So it will kind of look like upward sloping curve. And then for block B, it's also going to be somewhere between 0 and mg, and have a max at mg, because when theta is 90 degrees, the tension between the blocks will be 0, as it will just be in free fall, and they will have the same acceleration. Describe how the graph for block A and part C would change if the string in block B were removed and block A were released from rest on the incline. Justify your answer. So the best way to answer this is to think about what would happen when we remove block B from the system in general, not about the graph. So when we remove block B from the system, at 0 degrees there's no tension, right? There's no tension because there's no string, no block B, and therefore at theta equals 0 degrees, you will just have a horizontal plane where the normal force and gravity are equal, and there is no net force, right? Now at 90 degrees, what would happen is it would still be 4mg, because the block would be in free fall just as it was before. So what mostly changes is the shape of the graph looks more like a sine curve because there's no tension, and also it starts at 0 degrees and not between 0 and mg. So once I finish writing this out, I could also read it out to you too. So the graph for block A would be different, as a net force, the graph for block A would start at a net force of 0, as an angle of 0 degrees would mean the block is at rest on a horizontal plane, and therefore so normal force and weight would cancel out to 0. We would also have a net force of 4mg at 90 degrees, since the block would just be in free fall. Just writing those few last words here. And that just means that gravity is the only force acting on it.